here, that is this convexity of this feasible region. Okay, so the important property is that feasible region should be convex like this. So if we take any 2 point and draw a line, then the interpolated point should lie inside the line. Okay, and also intersection of 2 convex set will give another convex set. So let us see, as per the linear programming problem, we already studied that the typical linear programming problem will give polygonal feasible regions. Okay, so that will be convex because if you draw any line like this, it will be fitting inside the polygon. But suppose you give the constraint combinations in such a way that you get a non-convex feasible region. Okay, so you can see that this part is non-convex. Okay, because there is a hole in the feasible region. So then this will cause problems in the linear programming problem. Okay, because in the linear programming problem, we are told that all the vertices are possible solution because the objective function will just touch there. So if you apply the logic here, okay, if you apply the logic here, then the algorithm will say all these vertices are solutions. But that is not right, because suppose if it says...
Professor, sorry to interrupt. Your cursor is not coming here. Are you pointing anything?
No, I am only drawing in red.
So the red color drawing is not visible to us.
But I am able to see. Okay.
Roshan, you have to able to see?
Huh?
Anybody else is able to see?
No, it's not.
No, it's
No,
not.
not visible.
Probably he is to launch again, mostly.
Okay, wait, I will load again. PPT and load again. Okay. Okay, so now let me draw with cursor. Okay, are you using split screen or single screen?
Single screen only.
No, that PPT, is it 2 slides you are seeing side by side or single slide you are seeing?
Single slides.
Huh?
Single slides.
Okay. Okay, now let me see if the... are you able to see now, red?
Yes.
Yes, sir. Yes, sir.
Okay, so this is the typical polygonal feasible region of linear programming problems. So originally we studied that all these vertices are the solutions because the objective function will just touch one vertex. So if we use this type of algorithm for this non-convex polygonal region, then the algorithm will predict that these vertices are also solutions. Then what will happen is that the objective function will pass like this and all these points will be solutions. Okay, all these points will be solutions which the algorithm doesn't know. So the feasible region must be convex like this. Otherwise, many algorithms will not work. It will give wrong results. Okay, then objective function, convexity of objective function. So a feasible region should be convex and objective function also should be convex. So first we look at convexity of single variable function, that is x versus f of x. So a function is convex in the range A to B if there is only one convex bulge in that region or only one minima between A and B. So that is the meaning of convexity of objective function within the range A to B. So what is the practical definition of this convexity? Instead of saying it should have only one minima, there's a more practical definition. So suppose this is your objective function And if it is convex within a certain range, say A to B, then what you do is that you take any 2 points, x1, x2, then you find f of x1 and f of x2, then any interpolated points on the line joining f of x1 and f of x2 must lie above the curve. Okay. So none of these points should touch this curve. So all these points should be above the curve in between f of x1 and f of x2. So then it will be convex within that range. So you can see that if a function is not convex like this, so this is not convex. Okay, because it has two bulges. Okay, then if you apply this definition, that is, I take 2 points x1, x2, I draw the line, then all these interpolated points are lying below the curve. So this definition is a good definition. Okay, it is helpful to detecting non-convex curves. Okay, then there is a mathematical definition of convex function given in the textbook. We'll just look at it, although it is not necessary to study this for the exam. Okay, so suppose I have a curve like this. Okay, how to check the convexity within this range? So what you have to do is that you take any 2 points, x1 and x2, you find f of x1 and f of x2. Okay, so this is f of x1, this is f of x2. So this is f of x the whole bar. That is average of f of x1 and f of x2. That is this thing. Okay, then here you find x bar. X bar is the average of x1 and x2, and you find f of x bar. Okay, so suppose this is 5, this is 10, so x bar is 7.5, you find f of 7.5. Okay, suppose this is 100, this is 150, so this side will be 125. Okay, so this f of 7.5 should be below this 125. That is the formal or mathematical definition of a convex function. Okay, so it is written like this. Okay, so that x bar be the interpolated points between x1 and x2, and f of x the whole bar is the size interpolated in the same ratio between f of x1 and f of x2, and then for a convex function this f of x bar should lie below f of x the whole bar. Okay, so that is the mathematical definition of convex function. And in case of a straight line, this condition is just satisfied. If you take a straight line, this f of x the whole bar will coincide with f of x bar. So it is like a borderline case, and it is accepted as a straight line is accepted as a convex curve, because f of x the whole bar will just coincide with f of x the whole bar. Okay, the straight line is limiting case of a convex curve in 2D. Now next is concept of convexity can be extended to two variables functions. So their objective function will be a surface. So you can see a objective function surface here. So this has only one cup. Okay, one cup or one bulge within the range of x1, y1 and x2, y2. So this is the range. Okay, this is the range of x, this is the range of y. Okay, okay, so it has only one cup within this range, so this is convex. Okay. But how do you how do you practically define convexity of a surface? You can define it in the same way you define for a curve. So you take 2 points, x1, y1, x2, y2, you draw straight line between them, and it should not touch any of the surfaces like this. Okay, so this is the surface. So all these points should be above the surface. So this is how it is. Convexity is extended to 3 dimension. three-dimensional space. Okay, okay, now suppose it is not convex, it has two bulges like this. Okay, then if you take x1, y1, x2, y2 and draw this line, then some of these points will go below this surface. So this is not convex. And another thing is that if a objective function is convex, then the contours of f of xy on the xy plane will also be convex. So you can see this is that convex surface. And these are the circular contours. So this circular contours are also convex. Okay. Then a plane is also a limiting case of a convex surface. Earlier we saw that straight line is a limiting case of a convex curve. So in 3 dimension, a plane is also a limiting case of a convex surface, because if you take x1, y1, x2, y2, all these interpolated points will lie exactly on the plane. So, I mean, it's not going out of the plane, it is lying exactly on the plane. So, plane is a limiting case of a convex surface. Okay. So, after having studied this convexity of feasible region and convexity of objective function, we can understand what is the meaning of convex programming problem. So it says that if the feasible region is a convex set and the objective function is a convex function within that variable range, then the solution will have only one minimum within that variable range. Okay. There is also sometimes possibility of many equal minimum. So that we'll see. So you can see various cases here. So convex feasible region, so contours of convex objective function, it will touch at only exactly one point. So this is also convex feasible region. This is contours of convex objective function. It will touch exactly at one point. There will be only one solution. Similarly here, convex feasible region. This is the linear programming problem. So this objective function will touch at exactly one point. And then the other case where you can have multiple optima is this case. So this the line contours of the objective function are exactly touching this parallel side. And we studied that a line is actually a limiting case of convex function. So we cannot blame the objective function. Okay, in this case. So this is also, so this can also rarely occur in the convex objective function and convex feasible region. Okay, then some other general knowledge, just like convex function, there is also concave function. Concave function is, say a function f of xy is concave if minus f of xy is convex. So this is convex, so its negative will be concave. So the peculiarity of concave function is that within that range it will have only one maximum. Okay, only one maximum. Actually, nobody studies concave functions because people only study the convex functions. Okay. Okay, then mathematical text for convexity of objective function. The previous methods we studied are all graphical methods. In practice, nobody will draw the contour of objective function and pick any 2 points x1, x2 and check interpolated points to check if it is convex or not. There is a mathematical method to check convexity of objective function. Okay, so the function of n variables, that's x, y, z, is convex only if the second derivative matrix or Hessian matrix is positive definite or positive semi-definite for all x, y values within that range. So this is second derivative matrix. Okay, second derivative matrix. So diagonal elements are all that direct derivative, that is partial squared f by partial x squared, partial squared f by partial y squared, partial squared f by partial z squared, and the off diagonal terms have like partial x, partial z, partial x, partial y, etc. So this should be positive definite or positive semi-definite. So what is the meaning of positive definite? The positive definite means all the eigenvalues of this matrix must be greater than 0. Positive semi-definite means all the eigenvalues of the matrix should be greater than or equal to 0. So that is one definition. So in the exam, if it is difficult to find eigenvalues, there is a alternative definition here. Okay, you can check if the matrix is positive definite if diagonal elements are positive and leading principal determinants are positive. Then similarly for positive semi-definite, diagonal elements are non-negative, that is it can be 0 or positive. Leading principal determinants are also 0 or positive. So what is the meaning of this leading principal determinants? So that we'll see. Okay. That we'll see in the next slide. What is leading principal determinants? Okay, then for single variable objective function, the above condition reduces to the condition for convexity is that partials d squared f by dx squared is greater than or equal to 0. That is, there's only one variable x, then there is only one term. Okay, only one term is here. Okay, now we'll see what is the meaning of leading principal determinant. Sometimes to solve problem that is required. So leading principal determinants. So for a n into n matrix, there will be n leading principal determinants which are obtained by deleting successively the row and column starting from the last. So this is our matrix. The first leading determinant is this. Okay, whatever elements you see here is the first leading determinant. And the second leading determinant is obtained by deleting last row and column. So that is this thing. The third leading determinant is obtained by relating this 4 rows and columns like this. So this should be positive.
n cross n na 3 cross 3 ன்னு சொல்றாரு. 3 னா 3 determinant அப்படி இருந்து தான் ஆகணும். ஃபர்ஸ்ட் இது by default
positive or 0. Okay.
செகண்ட்ல கிராஸ் மட்டும் எடுக்கறீங்க. கேக்குதா?
Sir, how we can reduce it to 2 by 2? Means how we have to delete that part?
No, that is the meaning of leading principal determinant. First leading, okay. Leading determinant 1 is obtained by finding determinant of whole matrix. Leading determinant 2 is obtained by deleting last row and column. Leading determinant 3 is obtained by deleting this last 2 rows and column. That is the definition of leading principal determinant. Okay.
Okay.
And that alone is not enough. Diagonal element should also be positive. Only then it is positive definite. Okay. So if you don't want to do all this, you can find eigenvalues of this matrix. Lambda 1, lambda 2, lambda 3. That should be 0 or positive.
Oh, okay. Okay.
Okay. And what I showed in the last slide, no? Either you do this or you do this. Okay. Sometimes you may have to solve cubic equation here. Okay. If xy z is there, you may have to solve cubic equation. To avoid that, you can use this method. Okay. Anyway, we look at some examples. So first examples to test convexity of single variable objective function. So test the convexity of the single variable objective function. It's a function of x. X is varying from -5 to 5. So test of convexity for single variable function is second derivative should be greater than or equal to 0 in the entire range of x. So second derivative here is 4 minus 6x. If that should be greater than or equal to 0, x should be less than 2 by 3. So x less than 2 by 3 is the convex range. So you can see here So this is x 2 by 3, x is less than 2 by 3. So you can say this is a convex, okay? Convex and, okay, from here it is concave, okay. Then, so you can see how the convex part looks like. So this is only one minima. Okay, then another example, test the convexity of this objective function for the entire range of x, that is minus infinity to plus infinity. So this is the expression for second derivative. So if we equate it to 0, then condition for convexity is satisfied if x is greater than or equal to 1. So let us plot and see how the convex part look like. So it is looking like this. So this is the convex region. X is greater than or equal to 1. So this is the only minima. Okay, this is actually concave. This side looks like concave. This is convex. Okay. So next we go to problem where you check convexity of objective function in 3 variables. So the convexity of objective function in 3 variables we cannot visualize. Okay, because that space we cannot visualize. We can only check it by using the matrix. So an objective function is given like this. Okay. So to check the convexity, you find second derivative matrix. So it is 6 minus 2 minus 2 minus 2 4 2 etc. This is second derivative matrix. Okay. Matrix. So you have to check if it is positive definite or positive semi-definite. So we'll use this method of leading principle, checking the leading principle determinants. So this is the first leading principle determinant. So that determinant is 16, greater than 0. This is second leading principle determinant, which is obtained by deleting last row and column. That value is 20. So that is also greater than 0. Then next is 6. That is, you delete these two and left with 6. 6 is also greater than or equal to 0. And the diagonal elements are also greater than or equal to 0. So it is positive definite and it is a convex objective function. The other method is to find all the 3 eigenvalues of this matrix and check if they are greater than or equal to 0. Okay, then another problem. So this is a full optimization problem. So objective function is given, constraint is given. So check if the following optimization problem is convex or not. So you have to check convexity of objective function and check convexity of feasible region. Both have to be checked. So first check convexity of the feasible region. Now to check convexity of the feasible region, there is no shortcut. You have to plot it and check. So if you plot these two, this feasible region, you will get something like this. Okay, this is x plus 3y less than or equal to 6, and this is other one 5x plus 2y less than or equal to 10. So you will get a convex feasible region like this. So feasible region is convex. Okay, there is no issue with that. So next you have to check convexity of objective function. So that you have to try the matrix plus a 2 variable problem. So this is the second derivative matrix. So you get this minus 6x 0 minus 4. So you can see that the diagonal elements have negative sign. So this minus 6x is okay because for certain values of x, minus 6x will become positive. But this minus 4 will be always minus 4. It will not go away. So to the diagonal element, at least one diagonal element is always negative. So objective function is not convex and it can have many local minima. So what will happen is that, so your feasible region is convex like this. Okay, so your objective function is not convex. So it is, contour can come like this. It can touch at maybe 2 points like this. Okay, that can occur. So it is not, so you can't say it has only one local minima for sure. It can have multiple local minima. And is the following problem convex or not? Okay, minimize this objective function subject to this constraint. So constraint readily gives a convex region because it's a line boundary. I think this constraint will look something like this. Okay, this is that x plus y minus 2 less than or equal to 0. Okay, it will look like this. So the constraint is convex, no doubt. Okay, then what about objective function? Okay,
This is
so
circle.
yeah, it will be circle. So you can also predict that way. This is actually
It's a convex.
contours centered around 1.5, 1.5. Okay, 1.5, 1.5, and it will be convex. Okay, but let us check with matrix because that is the proper method. Okay, okay. So you check this. You draw this matrix. You obtain this matrix. Diagonal elements are positive. Then leading the principal determinant 1 is 4. That is positive. Then second leading principal determinant is 2. That is greater than 0. So it is positive, definite, and convex. So contours will come like this, and it will, you will get only one solution like this. I think we can stop here now. The single variable optimization algorithm we can start in the next class, okay? Because that's that if you start, it will not, that algorithms are a bit complicated. We start this in the next class. Okay.
Sir, just one query. Am I audible?
Okay.
You have any practical example of having many equal minima for a CPP problem?
Practical example, I don't have this. That later in the end, we can do with the MATLAB toolbox, we can try to do. Okay.
Okay,
I'll
sir.
give
Okay.
some worked examples with MATLAB toolbox. Okay.
Yep.
So with objective function and constraint, there you have to program it and plot feasible region and all that. And also you have to use the toolbox objective, toolbox subroutine to find the answers. And that should match with the graphical result answers. So there you will experience all these issues firsthand.
During our exam, it will be only written exam, or we'll have the MATLAB also, sir?
It will be only written exam,
Okay.
hand
Okay.
calculations.
Understood, sir.
You are allowed to bring the formulas also. Okay.
Clear, sir.
Formulas. If it is online exam, it's okay. You can look at lecture notes. It's offline, naturally you cannot bring all the PPT slides with you. You can write down the formulas and bring as extra sheet.
Got it, sir. Okay.
That I'll tell at that time.
Yeah, clear.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you, sir.
Very. Hello.
Thank you, sir.
Thank you. Thank you. I'm trying to.
Sir, just one query additionally.
Oh,
Yeah, sir, in the previous example, you have shown one graphal method.
oh.
And after that, when we checked with mathematical, it was found to be non-convex.
Which
the
one?
The contour also you have drawn as a curve.
Oh,
So how we will come to know about that contour shape?
which example?
The last example, sir.
Last one.
Let me see this. This thing is, it is a bit. not able to escape from this circuit. It is asking keep, discard, and all these things.
It is asking you to whether keep the red color drawings, whatever you are doing, or
Okay,
maybe we
okay,
can.
okay. So which one? The one which I drew the two touching things. Huh?
Yeah, sir.
Yes,
The
sir.
last example wherein there was a circle equation and there was a line equation.
This one. This one.
Sir,
Okay,
we are still seeing the single variable optimization algorithm slide. We are not able to see that slide you're presenting.
Wait. I think so. It's, okay, now I started again. Has it changed now or what?
No, sir.
Yet to reflect, sir. Yet to reflect.
Okay. I don't know if the.
Sir, I think you need to stop sharing and then.
Yeah, I'll stop sharing and share once more. Entire screen. Okay. Okay, let me again hop to 2.
Yes.
Screen is visible, sir.
Oh, okay. What do you want to see? This one, huh? Or this one?
The previous one. The previous one.
This one.
Yes, exactly. So
That I roughly drew. I just roughly drew for illustration. What will happen if objective function contours are not convex? It can bend and touch at 2-3 places simultaneously.
okay. So once
Yeah, I drew something like this. Okay, so this is this 2 lines. There's something like this. If it objective function is convex, the contours will touch only at one point. If it is non-convex, it can come like this or something. Okay, it can touch at maybe 2 or 3 points. I'm just saying as a general.
yeah,
sketch.
got it.
Not
got
for
it.
this.
I got it.
Okay, that's the meaning of the both should be convex. Visible region should be convex, and the objective function should also be convex. Only then at one point it will touch.
Okay. Okay. Got
Clear,
it.
sir.
Thanks.
Okay. Okay, then tomorrow we will continue.
Thank you, sir. Thank you, sir.
Stop recording. Where is that?